Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. For those challenged with promoting the use of machine learning in an organization and making it more accessible, one key to success is supporting data scientists and machine learning engineers with modern processes, tooling, and platforms. This is a topic we're super excited to address here on the podcast with the AI Platforms podcast series that you're currently listening to, as well as a series of eBooks that we'll be publishing on the topic. The first of these books takes a bottoms-up look at AI platforms and is focused on the open source Kubernetes project, which is used to deliver scalable machine learning infrastructure at places like Airbnb, Booking.com, and OpenAI. The second book in the series looks at scaling data science and machine learning engineering from the top down, exploring the internal platforms that companies like Airbnb, Facebook, and Uber have built, and what enterprises can learn from them. If these are topics you're interested in, and especially if part of your job involves making machine learning more accessible, I'd encourage you to visit twimlai.com/AI platforms and sign up to be notified as soon as these books are published. If you found yourself saying Kuber what, Kuber who when listening to this intro, this is the show for you. In this episode of our AI Platform series, we're joined by OpenAI's head of infrastructure, Christopher Berner. Chris has played a key role in overhauling OpenAI's deep learning infrastructure in the course of his 2 years with the company. In our conversation, we discussed the evolution of OpenAI's deep learning platform, the core principles which have guided that evolution, and its current architecture. We dig deep into their use of Kubernetes and discuss various ecosystem players and projects that support running deep learning at scale. And now, on to the show. All right, everyone, I am on the line with Christopher Berner. Chris is the head of infrastructure at OpenAI. Chris, welcome to This Week in Machine Learning and AI.
Thanks a lot.
Awesome. So why don't we get started by having you tell us a little bit about your background. You are coming up on almost 2 years at OpenAI now. How did you get to OpenAI?
Yeah, well, let's see. So before OpenAI, I was at Facebook. I worked there for about 4.5 years. And before that, worked at a couple startups. At Facebook, I worked on the newsfeed ranking team for about a year. So got just a little bit of sort of introductory experience in machine learning. And then I worked in the data infrastructure team. Worked on a distributed SQL query engine called Presto, which is open source. So have a fair bit of background in big data analytics and data warehousing, and that has certainly helped me get up to speed with all of the large-scale infrastructure that's required for deep learning these days. And just been learning all about the infrastructure that you need for machine learning training and specialized infrastructure there.
And so OpenAI is certainly doing machine learning at large scale. Maybe we can start out by having you, I've talked to several people from OpenAI on the podcast before, but maybe you can start by providing an overview of some of the larger projects that kind of stress the need for a platform for machine learning at OpenAI.
Yeah, well, certainly our largest project is our Data 2 research project. And in the past few months, we've announced a bunch of the results with OpenAI 5 there. And that's a very large system, trains on hundreds of GPUs and over 100,000 virtual CPU cores. Runs in one of our clusters in Google Compute engine. And that's definitely our largest. We have several other projects that are also quite large, though. Our robotics team also does some very large-scale training. I've actually done a little bit of work on large-scale ImageNet training. That's like 100 or 200 GPUs. I'd say kind of all of our teams have things that are on the medium to large size, but data is definitely our largest.
Nice, nice. And I spoke to Christy not too long ago about the Dota project, so I'd refer anyone who wants to hear more about that to that interview. Um, in terms of supporting these types of projects, when you started at OpenAI, was there much established, or have you kind of had a hand in building it up from scratch?
Yeah, some of both. So definitely, we already had Kubernetes clusters set up when I joined. They were definitely architected differently than they are today. And yeah, I've been involved in changing the architecture of them to make them scale better and also isolate faults better. So that was in place. We've also made some changes in terms of our storage technologies and a bunch of the frameworks that we use for running experiments. I think that's actually one of the areas that we've seen the largest changes. We had 2 or 3 different frameworks that existed when I joined, and I don't think any of those are still around. We've moved on to completely different ones. So yeah, so a mix of things that still exist and a bunch that has changed.
You mentioned that a big part of the change was driven around scalability and I think it was reliability. Those are a couple of things that have driven change. But, taking a step back, when you think about the characteristics that you're trying to be able to provide to the research teams from an infrastructure perspective, those the two only and most important things, or are there a set of things that you think that they require of you to be able to do their jobs effectively?
Yeah, so those are definitely 2 very important ones. There's a couple others that I would add. One is access to cutting edge hardware. And we run some machines in our own data centers because we want access to hardware that's not available in the cloud. And so, yeah, that's another dimension. And then, yeah, I guess sort of another aspect, but is more on the tooling side, is just ease of use. That people want to be able to launch their experiments quickly and iterate quickly. And so that's another important aspect of infrastructure.
And it sounds like the support for the framework of choice for the researchers is another one, in that you've already kind of gone through a transition on the framework side. You don't want to lock them into a specific choice there.
Yeah, we try to provide as much flexibility as possible to our researchers. Like I mentioned, there were some old research tools that I don't think people are using now because they've invented new ones that are better. Similarly, we don't want to be limited to running experiments just in the cloud. And that's one of the benefits that we see from Kubernetes, is that it's very easy to port your experiments from the cloud to our on-premise clusters, where we may have access to different hardware. And it makes that transition pretty seamless.
So the frameworks that you mentioned that folks weren't using, that you transitioned from, were those internal frameworks, or are these all open source frameworks, but you're just using different ones now? Are we talking about things like TensorFlow and PyTorch, or are we talking about internal tools that have been developed at OpenAI?
Yeah, so those particular ones were internal.
Okay.
It was a few different frameworks for running and managing experiments and visualizing the results from them and things like that. And now I'd say like TensorBoard is pretty popular. That's kind of replaced some of the need for our custom tooling in one particular area. Also TensorFlow, I'd say that's definitely our most popular sort of machine learning framework. I'd guess that 90% of our code is probably TensorFlow. But there's also starting to be a significant contingent of people who are using PyTorch. So some amount of change in that area too.
Okay. Can you, before we dive into, kind of an architectural overview of the platform that you've set up, can you walk us through kind of the level above that, like the the workflow or the processes as you see it that you're trying to support? So, for example, you mentioned experiment management and how some of the tooling there is shifted from internal to TensorBoard. What are the ways in which you think about the functional requirements of the machine learning researchers that you're supporting?
Yeah, certainly. Yeah, I guess at a really high level, pretty much everything that we do is research and experimentation and training models, which makes us a little bit different than a lot of other companies that are doing machine learning, because they're often then going on to integrate those into a product and deploy that to all of their users, whereas we're really just focused on the research side of things. And so we try to optimize our tools for iterating quickly and exploring a lot of different research directions, and providing the flexibility to do experiments in all different areas. So we've got a number of teams that do reinforcement learning, but we also have teams doing supervised learning and unsupervised learning. So a whole bunch of different types of problems that they're trying to solve. But kind of all of it comes back to training models and collecting the results from them, and then being able to iterate quickly on the next version of their research ideas.
Okay. So whereas in a non-research enterprise, something, some of the front end work of integrating with data warehouses and things like that isn't so critical for you. And some of the back end model management tasks where you're trying to manage productionized models, is also not as critical for you, or not at all critical for you. The part in the middle, this experiment management piece, is, that has to be done really well to make sure that the folks you're supporting are able to work most efficiently.
Mm-hmm. Yeah, exactly. Because that's pretty much all that we do. And so that's really where we focus our effort.
And when you think of that job, from a, quote unquote head of infrastructure perspective, are you thinking of it? I guess I had this picture in my head of, infrastructure looking down, like, hardware and platforms and frameworks, and, infrastructure looking up, like tools that manage that process of experiment management, for example. Or are you kind of, top to bottom there, or are you, just the bottom part? Or
yeah, I would say that we do kind of a bit of everything, but for the most part, we're focused on providing the compute clusters and, I guess also running like the storage clusters and other things that are related, but so sort of providing, the bottom layers of making sure that everyone has access to the compute and the hardware that they need. But we do also work a bit on the tooling side. Most of our experimentation management tools have been developed by our research teams, but we certainly help maintain a few of those and help support them with new features. And so I think infrastructure's role has kind of expanded, and actually in some ways, I suppose, contracted too. We used to have other tools that we ran and managed, and now we've decided that those aren't so useful, so we no longer run those. But kind of the main focus of the team is on providing really big compute clusters. But then we've also got a lot of other responsibilities on the tooling side and other places that we work on.
One of the things that I found interesting when I look at what you're doing, you've published, OpenAI has published quite a bit on its infrastructure and some of the things that it's done. And one of the things that I found really interesting is the very strong commitment to kind of this multi-cloud world. You've got experiments running on Google, you've got experiments running on Azure, you've got experiments running on AWS, and of course, on premises. Can you talk a little bit about, the motivation there, and what's driven the need to support, what has got to be a more complex environment than just standardizing in one place?
Yeah, for sure. I guess there's kind of a few different factors. So one, like I mentioned, is access to cutting edge hardware. So we can get whatever we want in our on-prem clusters, but the cloud also has a lot of benefits. You can quickly scale things up. They've got lots of nice APIs and auxiliary services that you can take advantage of. And So we like to have a presence with all of the major cloud providers so that when they launch a new type of NVIDIA GPU, or when Google announces their new TPUs, we want to be sure that we have access to those and that we can use them. And so that's one thing that drives our multi-cloud strategy. Another part of it is strategic partnerships and economics. We want to be able to take advantage of whatever cloud we can get the best pricing in. And so that certainly has advantages to being able to move our workloads between clouds and our own cluster, of course.
And so you've got these disparate research workloads. You've got these multiple infrastructure environments, clouds, plus your on-premises cluster. And as we've alluded to, Kubernetes is a part of the platform that ties all this together. Taking a step back from that, when you describe the platform for machine learning and deep learning at OpenAI, how do you describe it? What are the major pieces? Do you have names for things? Kind of walk us through the platform.
Yeah, for sure. So Kubernetes is a big piece of it. We run 3 different production clusters. We name all of our production clusters animals alphabetically. So the latest one, we're up to J now, which is Jaguar. So that's our newest one. We've got 2 others, Horse and Ibis. And so each of those is a Kubernetes cluster limited to a specific cloud and geographic region, or our on-prem cluster. And then sort of outside of that, we've got a number of tools. So the rapid experimentation tool is the one that our data research team developed. And that does sort of all of their experimentation management and provides a bunch of core building pieces for building their experiments as well. And that's one that our robotics team uses as well, and a couple other teams have experimented with. So that has really helped us, I'd say, move quickly and be able to launch new research experiments in the reinforcement learning space, because that's what that tool is optimized for.
Those core building pieces, can you give us some examples of what those are?
So like they've got an implementation of the PPO algorithm,
Of the what algorithm?
PPO, proximal policy optimization.
Got it. Okay.
Yeah. They've got a special implementation for synchronizing multiple GPUs that are spread across machines to do distributed training. A bunch of infrastructure just kind of for tracking the experiments, managing optimizers, managing tiers of machines that are running the environment, so like the Dota 2 game or a physics simulator, streaming that experience back to the optimizer machines. So kind of, managing the application level distributed system that has to do all the training.
Is that tool used for multiple experiments? And what's I'm curious how customized that is for a specific application or experiment, or if it's, can a new experiment kind of plug into it pretty easily and take advantage of all the different subcomponents that it offers?
Yeah, so it started out quite specialized for the Dota team, and then has expanded into a more general research tool that we're now using in a number of teams across the company. So the robotics team was the second team that started using it, and they've applied it to some of their robotic hand experiments. And that kind of turned out to be actually a similar problem. You replace the Dota 2 game with a physics simulator, and then a lot of the other components really fit together nicely. And now we've got at least one other team that's starting to use it. And they also, I believe, were able to get started really quickly, adapt it for their experiments. So I think a lot of our teams that are doing reinforcement learning are able to just move their experiments over to it really quickly.
Okay, cool. And so you mentioned you've got these 3 production clusters. And just to clarify, those are the 3 clusters on-prem, and then you've got additional clusters in the cloud. Is that right?
Oh, no, those are our 3 Kubernetes clusters. So one of them is on-prem, the other 2 are in the cloud.
Okay. And do the three clusters support presumably different research workloads simultaneously, or are they dedicated to a specific research workload, at a time?
Yeah, so it varies a bit. And because research projects kind of
Ebb and
they
flow,
change in
kind of?
scope over time, and they kind of ebb and flow in terms of their compute needs. It changes over time. Right at the moment, I believe all three clusters are being shared. I don't think any of them are dedicated to a single team at the moment. But it tends to be that like two or three teams will share one cluster, and that kind of makes it easier for them to know how much capacity they're going to be able to use, and it's just kind of easier for the infrastructure team also to know who it is that tends to be using each cluster. But at the moment, we run all three of them as shared clusters where anyone is free to use the capacity.
Taking a step back, so Kubernetes deals with containerized workloads. So the training workload, for example, needs to be containerized. That's not necessarily a skill that the typical data scientist has. One of the things that I read is that you've built some tooling that kind of does that for the researchers, so they don't have to get into the weeds in terms of containerizing their workloads. Can you talk a little bit about that?
Yeah, so one of the things that we try to do in general is provide a lot of flexibility in terms of tooling, because different teams and different researchers may have a different level of comfort with different tool sets. And so, people can use Kubernetes directly and build their Docker containers, and there's a bunch of people who are comfortable with that. And that's what they do. But then, there's also a set of people that prefer different types of interfaces, and maybe something that abstracts away all of the container details. And so another tool that we have called rcall, it handles all of the Docker containers, and in fact abstracts away sort of all of the Kubernetes details, so that you just have your Python code in a directory, and it knows where to find it, uploads it to the cluster, launches your containers, launches all your experiments, and then you can just focus on writing your TensorFlow and other Python code, and not even need to necessarily know that it's running inside a Docker container, or really that it's a Kubernetes cluster even.
And are the researchers there typically working with like Git repositories? Are they checking in code, and are you pulling from those Git repos when you're containerizing, or is it all just slurping stuff up from directories on the desktop?
We use Git quite extensively here. I guess, again, kind of a mix of things depending on the workflow that researchers find most convenient. Some of them, they're launching their experiments from code that they have locally, although that's almost always in a Git repository just from their local checkout. For other ones, maybe that it's built by a container build engine like Quay, and then we're deploying a container from that registry.
Earlier on, you mentioned that your use of Kubernetes has kind of evolved from when you started to today. Can you talk a little bit about that journey in general? How your use of Kubernetes has evolved as Kubernetes has evolved, what some of the big challenges with the different phases that you've gone through with your architecture have been, and how you've overcome those?
Yeah, it has changed in a number of ways. Certainly one is the scale. Our clusters have gotten way bigger than when I first started. But they've also sort of transitioned in their design. So when I first joined, the design that we had was a single production Kubernetes cluster, and it was a single multi-cloud cluster. So it spanned both AWS and Azure, and it sort of led to some behavior that was difficult to reason about. I don't think very many people run Kubernetes clusters where a single cluster is cross-cloud. And especially when we wanted to scale that up significantly to thousands of machines, we switched over to a model where we have multiple Kubernetes clusters, and each one is limited to a specific like physical region. So either our on-prem clusters or a availability zone in the cloud. And that made it a little easier to reason about some of the network aspects of it and not need to worry about some of the cross-cloud issues that we'd run into. So that really allowed us to scale more.
Can you give me an example of some of the issues that you ran into that kind of led to that shift? What were the kinds of things that you'd see?
Yeah, for sure. Well, so because we needed to run this cross-cloud, we had the control plane in AWS, and then we had a bunch of IPsec tunnels that connected to the other availability zones where the workers are running in. Mm-hmm. So we would have one set of workers running in like Azure's East Coast region and one in the West Coast region, and all of these would talk back to the Kubernetes control plane over this IPsec tunnel back in AWS. But this meant that IPsec tunnel was kind of a single point of failure. If that went down, not necessarily the entire cluster, but a large section of the cluster, because that whole group of workers would now be cut off from the control plane. So yeah, there was that problem. Then there was also the problem of if you wanted to use something like Amazon's file system, blanking on the name right now, EFS, I think it's called.
Oh, like EBS or S3?
Yeah. Well, S3, I guess, was a little bit less problematic, but certainly EBS.
Right.
That's something that you'd like to use. But now if some of your workers are in Azure, then you can only use it in like half your cluster. And then that's really confusing if you end up with sometimes you can use it and sometimes you can't. Mm-hmm. And then I guess one of the sort of most difficult to overcome problems was that if you scheduled your job into the cluster, it was possible for your job to get split so that half of it was in Azure and half of it was in AWS. And now if there was any network communication between them, that would just go very, very poorly.
Right. Right.
So you had to be very careful to specify that your job should only be in one cloud and not the other.
Okay.
But kind of all of that led to us just changing the model so that one Kubernetes cluster, one availability zone, then you don't have to worry about any of that.
Right. Yeah, it's interesting. I think in the Kubernetes community, certainly there's a lot of talk about hybrid cloud and multi-cloud, and even the ability to run a single Kubernetes cluster spanning multiple clouds. It's actually documented, not necessarily thoroughly, but it's there. Mm-hmm. But I don't get the impression that a lot of people do it for reasons like the ones that you're describing.
Yeah, it's some tough problems, and we were trying to solve them, pretty early in the development of Kubernetes. Mm-hmm. I imagine if we tried to do it now, the experience might be a little smoother, but some of those are just difficult problems to solve. Right. And then I guess the other area that our Kubernetes clusters have evolved significantly since I joined is our on-prem cluster. So that did not exist when I joined, and is one that we've been continuing to scale up, just as we have more and more demand for cutting-edge hardware that's not available in the clouds.
Mm-hmm. And so with that particular motivation front and center, in particular cutting edge hardware, for example, you have access to an NVIDIA DGX. I'm sure you have access to all the latest and greatest GPUs. Are you able to utilize Kubernetes features like labels and things like that to target workloads to these specific cutting edge hardware, or do you just kind of throw them all into the pool and let them land wherever they land, and kind of each incremental hardware piece just adds what it can bring?
Yeah, so we definitely do a bit of both. We use labels pretty extensively to provide finer grained control of exactly what hardware you get scheduled on as much as possible. We also try to keep our clusters homogeneous or mostly homogeneous so that you don't need to put too much thought into specifying exactly what you want. But yeah, it's a bit of both.
And do you find in general that the out-of-the-box Kubernetes scheduler does what you need for these types of workloads?
Yeah, so we've made some various tweaks to it, although we're still using the upstream scheduler and have just made like config changes and then sort of built some services on top of Kubernetes. we now have a system that uses the mutating webhooks feature, along with a controller and taints that sort of manage the resources in our cluster so that certain groups of machines can be dedicated to a certain team. And then when members of that team submit their pods, those pods will receive a toleration that allows them to run on those reserved machines.
Is that an alternative to using namespaces, or is that something that works in conjunction with namespaces to provide that feature?
Yeah, so it works in conjunction with namespaces. So here we have every researcher their own namespace, and then most teams also get their own namespace. They can have one if they ask for it. Just kind of depends on how they like to structure their workflow. And then, we integrate all of this back into our directory service so that it knows which people are on which teams. And then the pods in those namespaces can then be granted a toleration to run on capacity that's reserved for that team. So yeah, that's an area where we considered building all of this into a custom scheduler, but it seemed much easier to support if we just built it as a feature on top of the Kubernetes APIs that could then interact with the scheduler in the normal way.
Mm-hmm.
And I guess the one significant config change that we've made to the default Kubernetes scheduler is that the default one prefers to spread out the pods in like a deployment or a job as much as possible, which is good for fault tolerance. But for us, we tend to want the opposite. We would actually like as many pods as possible to be packed into single machines so that it leaves other machines completely empty. And that's good for two reasons. One is that if someone submits a bunch of small pods, we don't want them to fill up tiny pieces of every machine. We want them to be packed into a few so that there are whole machines available for people that want to use an entire machine. And then the other thing that it really helps us with is auto-scaling. So in our cloud clusters, we auto-scale them up and down depending on demand. And so you want to have your machines utilized as heavily as possible so that you can scale in the unused machines.
What does small mean in that context? Is it based on kind of a real-time metric like utilization, or is it something else?
Oh, yeah. So, in terms of small, I mean, like how many resources are being requested. So
Okay.
I would consider it small if you were requesting only one GPU, or maybe you're only requesting like half a dozen CPU cores. Whereas like our bigger pods, those are usually requesting 8 GPUs or maybe 4 GPUs, and then they're requesting dozens or maybe even 50 or 60 CPU cores.
Mm-hmm. How do you manage, if at all, the issue of folks, submitting jobs, i.e. pods, and reserving essentially these resources, but the pod's not actually, being idle essentially? Is that something that you actively deal with?
Yeah. So, I guess there's kind of two parts of it. We just kind of trust all of our researchers to use the cluster's resources well. And so we don't have any like checking of are you using the resources that you requested. But what we do have is a sort of internal billing system where we monitor how many pods you had running and how many resources they requested and how long those resources were requested for. And then it rolls up your billing every day, and you can see a report of this is how much money effectively you spent on experiments. And so, if you were leaving a bunch of pods running that were idle, it would show up in your bill.
And is that something that you had to build, or was that a project in the Kubernetes ecosystem that you were just able to kind of turn on and point to your clusters?
Yeah, it's something that we built, although it's actually very little code. We'll probably open source it if someone else doesn't open source a better solution that we end up switching to. But it's based on Prometheus. So Prometheus already monitors all of the metrics of what pods were running, when were they running for, how much did they request. And so really this is just a pretty simple Python script that queries Prometheus, aggregates all of that data, groups it by namespace, and then integrates with our directory service to figure out which team people's namespaces belong to, and then rolls up all the costs by team.
Okay, cool. And it sounds like you're running upstream, and you mentioned Prometheus. What other tools are you running or projects in conjunction with your use of Kubernetes?
Yeah, let's see. So we use the cluster autoscaler. So we use that for scaling our clusters. We use Prometheus. We use Heapster. Um, we use Flannel for an overlay network. We've got some deployments of Gluster, although that's sort of less directly related to Kubernetes. And yeah, I guess those are kind of the main ones.
Okay. You mentioned Gluster. What are the different ways that you deal with storage in the context of these clusters?
Yeah. So that's one of the areas that I feel like we have an okay solution now, but I'd really like us to have a great solution.
Mm-hmm. It's a tough problem.
It is a very tough problem. So we've got Gluster deployed, and it's been reasonably good. We haven't quite gotten the performance that we want out of it, but it's definitely convenient. Teams certainly have some data storage in S3, in Google Cloud Store, in Azure's Blob Store. So spread out over those. For our cloud Kubernetes clusters, we use whatever sort of EBS equivalent they have. Google, that's their persistent volumes. Those are really convenient. For our on-prem cluster, I think what we're going to end up deploying is Ceph, possibly through the Rook project. Mm-hmm. But we haven't started on that yet. So it's a little bit hard to say what we're going to end up with, but that seems like it has a lot of promise.
It sounds like then there's a strong inclination towards a distributed storage solution that kind of runs on the existing compute infrastructure as opposed to some standalone monolithic kind of NFS type of thing?
Yeah. So I guess what we have found, so I guess Gluster sort of falls more into the single shared file system like NFS. And what we found is that the performance hasn't been quite as good as what we want, although maybe that could be resolved by tuning some of the configuration settings or adding more hardware. But the other issue has been sort of fault domains, that when one team really starts hammering the storage, then it causes a disruption in service for everyone. And so one of the potential benefits that we see of something like Ceph is hopefully better fault isolation, where that won't happen because you'll have your separate remote block devices.
You mentioned Flannel for networking. How has dealing with the networking been since you've gone away from the multi-cloud? Has that kind of addressed all your issues, or is it still a challenge for you?
Yeah, I'd say that really simplified things. And these days, I don't worry too much about our networking. So Flannel has worked out nicely. We sort of integrate all of our clusters together via a VPN so that researchers can connect all of them very easily. And that's worked out well. And with our on-prem cluster, we've kind of figured out some of the performance aspects. Originally, when we had deployed Flannel, we deployed it in a way that wasn't as performant. But when we switched over to, so we're now using their direct routing feature, and that really resolved the performance problems that we were seeing there. So it's pretty much been a non-issue since we made some re-architectures to our clusters.
Okay. And one of the advantages of the single Kubernetes cluster as opposed to a federated would be that the researchers don't need to think about, where a particular workload goes. Have you found another way to abstract that, or do they just have to, did they target a specific cluster when they're deploying workloads?
Yeah, for sure. So our experimentation tools handle a little bit of that, of trying to abstract it away so that the researchers don't need to worry about it so much. Longer term, I've been sort of loosely following the upstream work that's being done in federated Kubernetes and how that all is going to work. I think at some point in the future, we're really hoping to switch over to a model like that, where there is a federated control plane that can then handle the scheduling so that it looks like a single cluster. But yeah, not there yet.
Right. Speaking of which, what's been your experience with Kubernetes as it evolves? How have changes on the Kubernetes side changed the way you use it? And maybe starting, did you run into any, hurdles early on that you had to, maybe develop around or, hack around that, Kubernetes eventually caught up with what your needs were, whether it's, in terms of its operation or scalability or reliability or things like that? Or, how's that whole experience been for you?
Yeah, definitely. So I'd say in general, super positive. The direction that Kubernetes has been going in has really just continued to address more and more of the pain points that we've seen. So yeah, I guess a few specific ones. We were probably one of the first people using Kubernetes to schedule GPU devices. And so we were using the alpha feature that added support for that, I believe, as soon as it was released. So we did have to build up some additional tooling for handling that and making it work seamlessly. Like in particular, the device drivers need to be mounted into your container. And so we had kind of a whole way of managing that with Symlink so that people could do it. Now that NVIDIA has released their device plugin, that's kind of all been automated for us. And so we switched over to that in all of our clusters, and it has simplified all of the management of the GPU devices there. And also, like on the scalability side, I think Kubernetes now officially has been tested up to like 5,000 nodes in the past. That was not as true, and we had to do some things to work around various scalability issues. But now a lot of that has just been handled by upstream, where they've optimized things.
You mentioned in terms of things that you're looking forward to, you mentioned some of the work around federated Kubernetes. Are there other things that you see on the horizon for Kubernetes or more broadly that ecosystem that you're excited about?
Yeah, definitely federated Kubernetes. Earlier I mentioned the Rook project. That's definitely one that I've been following and have quite a bit of an interest in. It looks like it might make it really easy to run Ceph in our on-prem clusters. And so that would be really exciting for us. So I'm hoping that project continues to get more traction. And beyond that, one of the things that we're looking at next is on the network side. We're planning to enable Rocky, the RDMA over converged Ethernet protocol in our on-prem clusters. And so this is one of the things that we can't get in the cloud. That's why we have our on-prem cluster.
So I'm not familiar with that one. You said Rocky?
Yeah.
And RDMA would be for remote memory access?
Yeah, exactly. Are you familiar with InfiniBand?
Oh, yeah, sure.
Yeah, okay. So Rocky is basically the same thing as InfiniBand, but it goes over Ethernet instead of the custom InfiniBand protocol.
Oh, cool.
Yeah. So it's really cool because then you can have all of your normal Ethernet workloads that are doing TCP or UDP or whatever, and then you can also have your RDMA applications that are going over exactly the same links. And yeah, so we're pretty excited about that. I think that's really going to improve both the throughput that we can get and also really cut down on latency.
Yeah, and InfiniBand's become pretty standard for some of these like high performance computing workloads because of its performance. Are you able to, how close do you get to that? And this is over 100G Ethernet?
Yeah, so I've done some testing on 100G Ethernet, and I believe have seen up to like 97% link utilization. So,
oh wow,
pretty awesome.
If I remember correctly, on the InfiniBand side, correct me if I'm mischaracterizing this, but my impression is that It's been limited to kind of these niche use cases like HPC because it requires that the applications need to be modified to take advantage of this memory access. Is that true? And will the same thing need to happen with Rocky?
Yeah, so it is true. And yes, the same thing will need to happen.
But at least you don't need a whole separate network infrastructure.
Right. Yeah. At least you don't need to buy completely new network cards and new switches and everything.
Yeah. Okay.
So then it can just happen at the application level. And really, what I'm hoping will happen is that we can handle all of it in the framework. And then you'll just have like a, op that you plug into your TensorFlow graph, which is the, all reduce over RDMA operation. And then people that are doing research won't have to worry about any of that. But that's still to be seen how that works out and how all of this is going to integrate into the Kubernetes ecosystem.
Nice. And you mentioned something that made me realize that one area that we skipped was how you're doing distributed training. Can you talk a little bit about that? There's a number of solutions for TensorFlow, for example. There's out of the box, there's Horovod, there are some others. Like how have you approached distributed training?
Yeah. So that's one where we have a number of different approaches. So we're definitely using Horovod. I've used it a bit. I know a bunch of other teams are using it. It's worked out quite well for us. We have some people that are just like directly using MPI for Pi. I think that has also worked well. I believe there's at least one like custom implementation of AllReduce that one of our teams has written. So yeah, kind of a few different solutions. Haven't converged on anything particular.
And the idea is in part because everything is containerized. They just containerize the components of their distributed training, deploy them out via Kubernetes, and it all kind of works like anything else.
Yep, exactly.
Cool. Well, any thoughts or words of wisdom for folks that are interested in Kubernetes as a platform for ML and DL and just getting started?
Yeah, I mean, I'd say that the portability aspect of it and just the ease of running it and scaling it is something that has really benefited us a lot. So, especially if those are important factors, I'd recommend it.
And in terms of ease of running it, sometimes Kubernetes, or at least early on Kubernetes, had this reputation for not being particularly easy. Like what's the support burden on your team for supporting the cluster been like, or the clusters? Granted that you're operating at a pretty tremendous scale, but
yeah, well, and I would say that that early reputation did reflect our experience too. That when I joined, we had a lot of problems that we were resolving, and there was a pretty non-trivial support burden. Mm-hmm. But both as Kubernetes has evolved and as we have evolved our way of managing it and understood some of the aspects that you need to pay attention to, like etcd in particular, really want to make sure that you've provisioned enough IOPS and everything for that. Now we've gotten to the point where I would say there's very, very little maintenance burden. We have an on-call rotation, of course, but in terms of critical issues, I'd say it's rare that we have even one problem a month.
Oh, wow. So let me re-ask that last question about words of wisdom in light of, all of the kind of revealed wisdom over the past, coming up on 2 years now that's gone into allowing it to be easy to maintain. You mentioned make sure you provision enough IOPS to your etcd. What are some of the other things that, folks need to do in order to have a good experience managing Kubernetes for these kinds of workloads?
Yeah. So we actually published a whole blog post back in like January or February that talks about some of the top ones. So yeah, definitely etcd is one of those. And most of these, they're really issues that you're only going to hit once you go beyond a few hundred machines. So you can run it at a pretty good scale and not have to worry about much of it. But yeah, once you get into the 1,000 or multiple thousands of machines, there's a bunch of stuff to be aware of. So yeah, etcd was one of them. We ran into some funny network issues. I spent a good couple of days learning all about ARP caches and how those work. And it was a protocol that I had learned about back in college and figured I'd never need to know about again. But very important to make sure that the ARP cache is big enough. The combination of using Flannel means that you need a significant amount of space in your ARP cache. If you've got thousands of containers that are talking to each other or talking to a single one, like the kubedns service. So there's a few other issues that we enumerated in that blog post, but it's really not stuff that you're going to hit until you've got many hundreds of machines.
Well, we'll link to that in the show notes for sure. Chris, thanks so much for taking the time to chat with me about this super interesting stuff.
Likewise. Yeah. Thanks so much for having me.
All right, everyone, that's our show for today. For more information on Christopher or any of the topics covered in this episode, head on over to twimlai.com/talk/199. To learn more about our AI platform series or to get our ebooks, visit twimlai.com/AI platforms. As always, thanks so much for listening and catch you next time.